Alright, so this is a video about data and models. Maybe the most important thing about science is making predictions, accurate predictions. We've become quite good at some of those, but have made absolutely zero progress on others. For example, I can open up my weather app and see that tomorrow morning there's a 30% chance of rain at 9 o'clock and a predicted temperature of about 14 degrees. This is a high level of detail and I can use this information for planning my day. On the other hand, if I'm interested in the probability of the next earthquake, all I could get is that a quake of at least magnitude 5 or more will occur every 200 years. Which is almost no information at all. Why this huge difference? Well, again, data and models. How do we predict the weather? Well, what is the weather? Basically, the state of the atmosphere at a given location and time. Mostly, we're not even interested in the entire description, but only in the temperature and whether it's gonna rain or snow. However, there are also phenomena like blizzards or hurricanes where we really want to predict where it will move next, or questions like that. The atmosphere is a large mass of air, a gas. Mostly nitrogen and oxygen plus some trace elements and a variable amount of water vapor. This gas is held on Earth by gravity and is heated up by thermal radiation from the sun. And this apparently basic setup can lead to a huge amount of different weather situations, depending on temperature, humidity, density, wind direction and strength, and so on and so on. The thing is, in principle, we can fully describe all these processes. We know exactly what a difference in temperature or density will cause, etc. So we can write down the equations that determine the weather. These equations aren't super complicated. The physics behind it is almost first semester stuff. But where it does get complicated is that all these quantities will differ both with time and location, and everything is connected. Even in a case where you have just a small number of equations, finding a solution becomes incredibly hard when they all interact with each other. In any realistic case, the only chance you have of solving such a system of equations is by using numerical methods and running those on a very fast computer. To achieve that, we divide the atmosphere into a grid, measure all the relevant quantities in each grid cell, and then use the approximation methods to calculate how this state will change. To get all these measurements, we use weather stations, ships, airplanes, radar stations, and even satellites. These measurements are then collected at a weather institute and fed into supercomputers to get a prediction of the future weather. As this process includes a lot of approximations and idealizations, the prediction becomes more uncertain the more long-term they are. We are pretty good at predicting the weather for the next couple of days, but beyond that, things become very inaccurate very quickly. The thing is, weather is a chaotic system, meaning that a future state is hypersensitive to the initial conditions. That's the so-called butterfly effect. Technically, a butterfly flapping its wings in Europe can cause a tornado in the US. This means that a true long-term weather prediction seems to be implausible, even in the distant future. Contrary to weather prediction, we have made almost no progress at all in earthquake predictions over the last decades. As earthquakes can inflict a great cost both in human life and in damage to infrastructure, a way to predict earthquakes is obviously highly sought after. Earthquakes are a consequence of plate tectonics. Both the continents and the oceans ride on gigantic plates that float on the inner layers of the Earth, which are made of liquid magma. These plates move very slowly, some millimeters or centimeters per year, and there are regions where two such plates collide. This will lead to one of them being pushed under the other, forming a so-called subduction zone. The other possibility is two plates moving alongside each other, forming a transform fault. In both cases, there are immense friction forces between the two plates, building up a great tension. This tension is released not gradually, but in single sudden events called earthquakes. Earthquakes cause seismic waves, shaking the ground within a certain radius depending on the strength of the earthquake. So, we at least have the advantage of knowing which regions are prone to earthquakes. Check out where tectonic plates collide and then compare this to the occurrence of earthquakes. The problem is that while we do understand these basics of earthquakes, we do not understand the details, so we cannot write down the earthquake equations. This also means we don't know what exactly we should measure. But even if we did know, it would probably be very hard to do, because these tectonic processes typically take place many kilometers beneath the surface. It would be hard to get there. One of the few things that we can measure are the vibrations at the surface, which can be picked up by a seismometer. So we can measure the effects of an earthquake while it is going on, but obviously this is too late for prediction. Most attempts at predicting earthquakes have been based on looking at past seismometer data of earthquakes and finding some kind of pattern in it. Recently also with the help of AI and machine learning. However, none of these models have been successful in predicting the next earthquake so far, raising the question whether earthquake prediction is even possible at all. Well, you know, theoretically, yes. But practically, ever? While both weather and earthquake prediction are interesting in their own right, there is a broader point that I'd like to make here. Another point of how science works and how it doesn't. Science! I call it the data model chain. Data is just measurements. You can have just a few or literally years worth of data across many locations or times. It just matters that you have it and you also understand the limitations of your measurements. A model is more interesting. It's a precise description of a process or a phenomenon. So not just a qualitative description like what I told you about earthquakes, but an exact mathematical description. For example, one equation used in weather models is the hydrostatic balance equation. dP over dC is equal to minus P over RT times G. Okay. Just bear with me for a second. You don't have to understand what each letter and each symbol means here. All you have to understand is that this is a precise description of how pressure varies with height. You don't have to understand what it says, you just have to understand that it exists and it tells us precisely how these two quantities are connected. And this is a vital point here. It's not enough to say that how pressure varies with height also depends on temperature. No, we need to know how exactly this varies with temperature. And these equations here contain this information precisely. Let me be very blunt to drive home this point. If you cannot write down an equation like this, you do not have a model. All you have is a basic idea. Okay, so we defined what data is and what a model is, but one ingredient is still missing, the chain. The chain is just repetition of the two, using new data to refine a model, or using a model to figure out what new data would be interesting. For example, we could start with either, but let's start with some data. Measurement results from an experiment. From this, we can deduce a model. Now, we can make a prediction for the outcome of another experiment, which we can perform to get new data, etc. This new data can now either be a confirmation for the model or it can be a restriction. So we might find an area where it ceases to apply. No model is applicable everywhere without restrictions. I actually made an entire video about this, which you can check out here. Here or something. Either way, any result gives us more information and we can use that to refine our model. This then goes on until we either have all the information that is relevant to us, or we lack the technology or funding to run further experiments. And this is what I call the data model chain. These repetitions, these iterations are essential for scientific models and the scientific method. What happens when you start breaking this chain? Well, you get models that are either weak or downright wrong. And unfortunately, this is not as unusual as it should be in academia today. For instance, you might do an experiment to get data and then infer a model from this. It's legit, right? Well, without further testing of this model, you really can't tell anything. It could be true, it could be just a statistical fluke, it could be whatever. You just don't know. This is only a legit first step, but if you stop there, you're not doing science. Imagine I do an experiment where a coin is flipped 10 times and I get heads, tails, heads, heads, tails, heads, tails, heads, tails, heads. That's a perfectly possible sequence. Now, looking at this result, I might be tempted to infer that whenever tossing a coin, you will, with a high likelihood, get the opposite of the last result. So, if you just got tails, you'll very likely get heads next time, etc. The only proof for this pattern is the data I used to find this very pattern, which is of course circular logic. What I really need to do is do more coin tosses and see if the predicted pattern really shows up again and again. Otherwise, all I'm doing is modeling random statistical aberrations that will not repeat. In science we call this fitting the noise. This is actually the reason why a shockingly large percentage of the results in psychology are not replicable, meaning if you run the experiment again, you will not get the same results. Mostly this situation arises because you're trying to make a model about something where you don't understand the mechanics, all the fine details that lead from A to B. In weather forecasting, we understand all the details in principle. We understand why and how air moves, what heat is and what it does, and what humidity means for cloud formation, etc., etc. We understand all the details, we understand the mechanism behind weather. For earthquakes, we understand only the basic outline of what is happening, but we cannot describe the details and cannot write down the equations, which means we don't understand the mechanism. All we have is some data points and all we can do is trying to deduce some laws straight from the raw data. Almost everything we get from this is fitting the noise. And by the way, this is also a huge limitation for AI pattern recognition and the big data analysis. Most correlations you will find anywhere are just noise. And AI just finds more of it. And lastly, we have some cases without even data. Especially some of the more modern and fashionable fields don't even bother with doing experiments to gather data. All they do is to provide a lens to look at the world. Unsurprisingly, this lets you see only what you wanted to see from the outset. This, of course, has nothing to do with science and should never be called science. All it does is damage the public perception of and trust in actual science.